Susie. I'm an associate professor here in the School of Physics, and I'm also the curator of digital elections in physics. And as many people know, this year's theme is around sciences and sustainability in physics. Let's swap that one out. There we go. And so many of you will have seen already 2 out of the 4 of our series of lectures for the year. So before I get going, actually, I'll just ask for a bit of a show of hands, because I know a lot of you come back every time. Was anyone here the earlier weeks of this year's series? Heaps. That's awesome. Who's been coming more than 5 years? Who's been coming more than 10 years? Wow. Okay. Anyone more than 20 years? Wow. That's like at least 10 people who've been coming to the July lectures more than 20 years. This is actually the 56th year of the July lectures in physics, but it is the first year that we've actually curated an interdisciplinary theme and trying to explore areas where physics really interconnects with society and with other areas of science. So for those of you who've been coming for many years, I know that's a bit of a change, but I think we're at a point where those conversations are really more important than ever. So before we get on with tonight's proceedings, I'd just like to acknowledge as well that we live and work on the lands of the Wurundjeri Woi-wurrung people of the Kulin Nation, and those are the unceded lands, of course. And just to recognise as well how much we're learning and always from the sustainable practices of Indigenous and First Nations people. So any First Nations people here are very, very welcome, and I look forward to further conversations in that direction. Okay, so we have an exciting lineup for you this evening, and if you've been coming this year, as many of you have, you'll know that this year I've asked a series of students who have been members of the Latrobe Fellowship, or recipients of the Latrobe Fellowship, which is the University of Melbourne's Sustainability Fellowship Scheme for students. And so we have another one of those tonight. So before I introduce her, I'm just going to show a quick video about what the Latrobe Fellowship Scheme is.
My action project is basically
tackling anthropocentrism in public health.
I'm looking at the intersection between agriculture and land management.
The Waddle Fellowship is the University of Melbourne's leadership development program for students with a passion in sustainability. Our students come from all across the university, regardless of what discipline they're studying, what type of degree that they're doing. They come to us because they have an understanding of some of the big issues that the world is currently facing. And they want to turn their knowledge into something really practical. They want to go out into the world, into their communities, and start to make a difference. And that's where the Waddle Fellowship comes in.
We've done leadership development, workshops, classes. It's a great networking opportunity. We have support and funding to develop our own action project. And I guess my idea of it is that we all come together, we grow and learn together, and then we can kind of go off into whatever industries or sectors we're in and try and sort of make it more sustainable in whatever way we can, and with our piece of the puzzle.
The Waddle Fellowship would have been possible without our generous corporate and philanthropic supporters, in particular our founding donors, the McCall-McBain Foundation. Without their catalytic support, we wouldn't be able to work on addressing some of the workforce and talent shortages that we have in reaching a just transition. We're really interested and open to working with any other organisations or philanthropic groups that might be interested in investing in our future by focusing in on people.
Well, the greatest contribution the university has is our students, and training our students through great education, through programs like the Waddle Fellowship program, where we're taking students from different disciplines and getting to learn how to become leaders around sustainability. And so the greatest impact this university is going to have are those students who, when they go out in the world, to make a big difference. And in this case, we need leaders to help us with all the sustainability challenges this world faces.
I'd say that it's not necessarily about what you've done, but what you want to do. You don't even need to come in with a project in mind. What they're really interested in is your motivation and your ability to have a vision and that desire to really improve your industry for the better.
And it's just a really great way to take whatever you've been learning in your degree and think about like those ideas and those like challenges that you think are really important to you, and be like, how do I develop the skills to actually start tackling those issues?
After every step, we were given kind of the next tool that we could use and incorporate into our project planning, which made it really helpful to design something big and grand.
So my project is called Gardens for Climate, and it's about helping homeowners and people who have gardens to prepare for the climate crisis.
My action project is creating videos about science, technology, engineering, and mathematics to educate primary school children about sustainability issues.
No matter your field, you can absolutely have an impact and get involved with sustainability.
If you want to make change and you need support and you need networks and you need ideas even, this is definitely the program to apply to.
Honestly, just go for it. This has been probably the highlight of my time at university.
Okay, and this evening's speaker from the Water Fellowship Program is Anka Oakley, who completed her Masters in Electrical Engineering at the end of last year, is now working in industry, and she's going to speak to us about her Water Fellowship Program. Please welcome her to the stage.
Good evening, everyone. My name is Anka, and I'm a first-year Grid Connections Engineer at WinLab. And before I lecture today, I would like to share some of my experiences as a Waddle Fellow. I joined the Waddle Fellowship in the second cohort in 2022 as I was studying a Masters in Electrical Engineering. About 6 months prior, I decided to rethink my career ambitions and focus on the renewable energy transition. And in that short time, I found there were numerous opportunities in the field to solve problems which are both at the forefront of some of the world's most critical challenges and very interesting from an electrical engineering standpoint. So this new focus reignited an optimism about action against climate change, and specifically my role in this fight. It was with this new focus that I applied for the Waddle Fellowship. So the Waddle Fellowship provides incentive, funding and support for a personal leadership development plan and a sustainability action project, which are to be completed over the program's duration. However, one of the most beneficial aspects is the connection with other Waddle Fellows, as they forced me out of my engineering bubble and challenged me to rethink how I engage with sustainability. The action project scope is very broad, and I initially didn't really know what I wanted to do, but after reading about a skills shortage in the energy transition, I ended up founding a student club here at the university called the Students in Renewable Energy, or SGIL, which builds student preparedness for careers in the energy transition. These skill shortages span a range of professions, but I thought I would start where I'm most familiar, with engineering and with the student community. I noticed many of my peers participate in extracurricular student project teams, and team members will tackle engineering challenges and develop skills and experience which will often kickstart their careers. At the time, there were no renewable energy projects, but from conversations with my friends, I found that, like me, many were interested in renewable energy but didn't see any opportunities to get involved. In creating SGIL, I could talk with my friends on topics of sustainable engineering, and with them we came up with 3 student-led projects. We also wanted to provide opportunities for students who could commit to a long-term project and those outside of engineering to see a little of how they could contribute to the energy transition. So we organised 2 site visits and even a debate and negotiation event. And these events were so much fun, and mainly due to the optimism, energy and ambition in those involved. And so when it was time to become an official UMSU club, we were able to get over 100 members in the first few weeks. I knew one of the challenges would be finding people to take SGIL on when I graduated at the end of last year, but I was overwhelmed with the enthusiasm and interest of students who put up their hands to form the first committee. And in the last 6 months, they've run 7 events, have 150 members, an industry mentorship and a community grant. I think the progress since January last year, when we first came up with the idea, is a testament to the strong interest of students to use their knowledge to help the planet. So if you're interested in engaging with SGIL in any capacity, as a member or a mentor or otherwise, then check out their socials via the QR code, or send me a message on LinkedIn. But thank you for your time and hope you enjoyed the lecture today.
And we'll be around at the end as well, so when we do the Q&A, do think of questions to ask Anna as well as to the main event and what you've come here for. Many of you will actually have to ask for show of hands again. Who's seen Professor Rachel Webster speak before in the July lectures? Lots of you, so she's a superstar to you. But you know that she's a superstar in astrophysics. So Rachel is a renowned professor of astrophysics. She's the head of astrophysics here at the University of Melbourne, running a group of about 60 people. She's had an illustrious career in that field, and in that sense, needs no introduction. But what does need introduction is that she's actually been on the side, working toward geothermal energy for about 15 years. I need to say no more. Professor Rachel Webster, welcome to the stage.
Good evening, everyone, and thank you, Susie, for that very generous introduction. So, in mid-June of this year, Australia's conversation about energy changed, and instead of what I would have thought was a clear path forward towards a substantially renewable future, a new proposal was floated suggesting an alternative way forward. In the end, we, the general public, are going to be asked to adjudicate on all of these ideas. And so tonight what I'd like to do is to present a slightly different view, but one that I believe can positively contribute to our opportunities going forward. So I want to just start with some of the headlines that we've seen in the newspapers in the last few days. And you'll see, importantly, that the Latrobe Valley features quite strongly in this dialogue. And that's, of course, because we've got coal-fired power stations down there with big transmission lines going there, and that's considered to be a good place to put another source of energy generation. But, of course, this is not without its controversies. And you know, for example, CSIRO has not been as enthusiastic about the idea as some of our politicians. So energy is top of mind. But of course, what I'm going to talk about today is geothermal energy, which is probably something that you know rather less about. So on this slide, I've got an outline of the things that I'm going to cover. I'm not going to go down through it, but note the image on the right-hand side here. It's a carving from Italy a couple of centuries ago, and it illustrates quite clearly that mankind has been using and enjoying the geothermal energy in all sorts of locations across the planet for many, many centuries. And so the question now is whether geothermal energy can be part of the mix that can take us forward to a more sustainable future. Now, before we get going, I want to talk about a little bit of terminology, introduce you to what geothermal energy is, and clearly acknowledge some of my collaborators in this work. And first of all, geothermal energy is not just one thing. It sort of it comes in different flavours, if you like. The simplest form is just heat pumps, and this is where you simply put energy into the ground, into the shallow ground. During the summer, typically, the ground heats up, and then later on in the winter you can take it back out again and heat your buildings. And so in the sense that the ground is just acting as a thermal battery. So that's quite straightforward and widely used, particularly in Europe. The next one that I've got there is direct use. And in these cases, what we have are aquifers underground that are warm or hot, and we access those aquifers and use the heat in the aquifers for various purposes. And the final one is actually generation of electricity. And of course, a lot of our energy needs are in fact or require electricity, and so if you like, that's the gold standard. That requires higher temperatures, quite high temperatures to be reasonably efficient. Now, the work that I've been doing is done very much in collaboration with Graham Beardsmore, and I'd certainly like to acknowledge him here today. But we've been supported for the last few years by Regional Development Victoria to the tune of about $1 million, which was a great relief, let me tell you, and has enabled us to do a lot more work than we were able to in the past. And we have very, very strong support from the Latrobe Valley Authority as well. And I'm going to mostly be talking about direct use geothermal because it's the low-hanging fruit. So this is where we learn about geothermal and hopefully in times going forward, we can then go deeper and hotter and actually generate electricity from the potential that we have in Australia, which is actually quite significant. Okay, so before we go any further, I just want to sort of frame the discussion, because energy is a complicated discussion, and there's many things that we have to think about when we start talking about it. So there's money, there's technology, and there's sustainability, and they all come into the conversation in quite different ways. So let's start with the money bit. Mostly the conversation is around, can we reduce the cost of energy? And it would be wonderful if we could do that. My personal view at the moment is that the reality is that it's probably going to cost us a bit more to get our energy, but that's going to be a small price to pay if in fact we can do it without generating carbon dioxide, because the costs that we're going to see with carbon dioxide emissions will be much, much greater than modest costs that we might see with rising energy costs. If we look at technologies, we have some mature technologies, so solar, wind, hydro, large nuclear reactors, and some geothermal resources, not in Australia, but Iceland, for example, generates all its electricity from geothermal. They have very different geological conditions than we do. And then there are emerging technologies as well. Nuclear fusion, I'd like to say it was emerging. At the moment it's just very expensive, but if it ever worked, that would be wonderful. And then of course carbon capture and storage, which is also very expensive and isn't really doing what we had hoped it might do. And then there is some development in geothermal as well. But I want to also make some more comments about renewable versus sustainable versus low carbon dioxide. And really what we've got to do, there's no question we need new energy infrastructure, and we've got choices. And the question is how to balance all these things up so that we can optimise the answer. So I just want to make some comments about sustainable and what it means, or in particular what it means to me. This is my physics bit over on the left-hand side here. You know, if you actually drill down, there are only three ways that we get energy, renewable energy. One is from the sun, that's fusion, okay? And then you can see down here that sunlight generates a lot of the other renewable resources that we use, but ultimately they all come from the sun, okay? The second one is the Earth's core, and that's fission. We have a very big nuclear reactor sitting at the middle of the planet. Fortunately, it's well shielded, it does its job, and it generates energy coming up towards the surface. And then finally, gravity does a bit for us as well. The sun and the moon, stretch and flex the oceans and the Earth's crust, and we can, in fact, grab that tidal energy sometimes, although that's not so easy. The other point I would make here is that, when we're thinking about solutions, timescales are really important. A lot of the timescales that people are putting forward are 3 years. That's how long we actually go between elections. We might go to 60 years, that's probably as long as you're a conscious adult, but really what we should be thinking about are solutions that run for thousands of years, because otherwise these problems are just going to re-emerge and worry people in future generations. So renewable energy, I've defined here as energy from a source that's not depleted when it's used, such as wind or solar. And sustainable energy is energy from a source that does not compromise future generations. And these are different things. Now, I'm concentrating very much on carbon dioxide, but some of the sustainability arguments are also around water and other things as well. So, those will be ignored tonight, but they shouldn't be ignored more broadly. Okay, so the definition of sustainable that I'm going to take tonight is simply to preserve the atmospheric temperature of the Earth within a narrow band and then there's a little rider on the end there which says forever. Okay, so in other words, we're not going to keep pushing it up. And when I wrote this on the slide, I thought, oh, I need to put a picture on here as well. And one of the things that I like talking about is sea level rises. And so I dug out the DECA Port Phillip Bay Coastal Hazard Assessment. And if you live down around St Kilda or somewhere down there, you should be thinking about moving if you want to have a long-term investment in your real estate because it's in trouble, and that's only with a 0.8 metre rise by 2050, by 2010. I've written 2010 there. What I mean to write is 2100, so I apologise for that. But and that 0.8 metre is probably quite conservative, I would expect at this stage. Anyway, and this one here, you know, one of the things about preparing these talks is you go and look at a whole lot of things that you haven't looked at before. This is the city of Port Phillip. As the sea level rises, the fraction of the city of Port Phillip that will go underwater, and you can see it gets to 35% quite quickly. So not a good place to live. Go somewhere higher in the metropolitan area. Okay. The next thing that I wanted to talk about just briefly was life cycle assessments of carbon dioxide emissions. There are many metrics that we use to think about renewable and sustainable energy, and this is one that isn't talked about a lot. And what an NRL, by the way, is the National Renewable Energy Laboratory in the USA, and so they do extremely good work. But the basic idea here is think about how much carbon dioxide is emitted with your energy, both in setting your energy generation source up, digging it up, transporting it, burning it, and then actually getting rid of the infrastructure at the end. So it's a whole life cycle assessment of the carbon dioxide emissions. This diagram is pretty interesting. And it's actually a calculation of grams of carbon dioxide emitted per kilowatt hour of emission. And you probably have some feeling for kilowatt hours because that's how your energy is actually measured and what you're charged for by your energy provider. When I looked into these figures, some of them are a bit rubbery because all they've done is to take published results, and so there are some vested interests in some of the published results. But nonetheless, it's pretty clear that gas, oil and coal do not fare so well, but we know that. Nuclear energy does fare pretty well on this metric. It's expensive, which is another metric, but on this particular metric it does do well. And of course so do all the energy sources that we know about, and geothermal energy that I'm talking about today is in there as well. Okay, so that's enough of a preamble, and let's now start talking about geothermal energy. What is it? Well, the most general definition is heat occurring naturally underground, which can be cost effectively carried, and usually by water, to the surface for some beneficial use. Okay, so here are some diagrams of different sorts of geothermal energy, and this is really just to drive home the point that I made earlier, that there's direct energy, there's electricity. This is an electrical generation, as is this one here, and it comes in all sorts of different forms. This one here is, of course, the nicest one. That's the Peninsula Springs Spa, which is definitely a place, if you haven't been there, it's actually very pleasant. All right, so let's just see why geothermal should be on the radar. It's basically zero or near zero carbon emissions. It replaces gas. In particular, the direct geothermal that I'll be talking about replaces gas or fossil fuels. It's reliable. It can operate 24/7. It has no storage costs. You don't need a battery or anything else to store it. Minimal visual and environmental impact. So the footprints of the sort of facilities I'm talking about are in the square meters area. You know, there's not a lot of ground, taken up with them. Very stable and low operating costs. The upfront costs are all are in the infrastructure, and drilling, as I'm going to keep emphasising, is where most of the cost is, drilling down to whatever the resource is. It's dispatchable, and what we mean by that is you can turn it on and off pretty quickly, and this is one of the issues, for instance, with nuclear power stations and with coal power stations. You can't ramp them up and down very quickly. It could foster new industries, and you'll see I've got an arrow there. Melbourne Food Bowl, this is one of my favourite ones for the Latrobe Valley. Could it become the Melbourne Food Bowl, which I think it has real potential. And then if we get into electricity generation, it's baseload power. And you will have heard people talking about nuclear as we need nuclear for baseload power. Geothermal would do this just as easily. Now, of course, there are limitations as well. It's not transportable. You are where you are. You go straight down, and you can move it a little bit, but you certainly don't want to be transporting the geothermal energy or hot water for great distances. And the most serious one is the lack of investment that we're facing, and this is an international problem. It's particularly true in Australia, but with modest amounts of investment, we could evolve and develop this industry into something really quite significant. Okay, so let's talk about Gippsland now. Why is Gippsland so exciting? You know, as I say, I mentioned Iceland. You know, they've got magma up near the surface. It's really hot. Magma, steam coming out and all the rest of it. Why is Australia interesting? We obviously don't have magma near the surface. Well, the irony here is that the coal in the Latrobe Valley is the answer. It turns out that coal, brown coal in particular, much better than black coal, is the best insulator on the surface of the planet. Okay, what does this mean? It means that the heat coming up from underneath, from the centre, the core of the Earth, gets trapped by the brown coal. And so under the brown coal, it is much hotter than it should be, okay? Which is extraordinary. So the bottom line is you can see the aquifer here. So this is a water aquifer, heat coming up, and there's the coal trapping it. And of course, so what we say is, why not leave the brown coal in the ground and then take advantage of this wonderful resource? So as we go along, I'm going to make it clear just how significant it is. The brown coal reserves in the Latrobe Valley, as we've always known, are the best on the planet. It's the thickest layer, closest to the surface, and it traps more heat close to the surface than anywhere else on the planet, which is quite remarkable. Okay, now I'm going to show you a couple of slides, sort of sciencey slides, but I want to just point out the really important things about this. This is the diagram that we had on our advertising, and it's just pointing out where the towns are in that area. I should say, so this is giving you temperatures at about 600 metres below the surface level. It's something called the lower tertiary aquifer. Even though, and this is a very recent publication by Geological Survey of Victoria, but you know, as scientists, we know that the data here is still very incomplete. So there may be much more than this. It's certainly not worse than this, but there may be much more than this. And you can see it's hot in a number of places around here. Now, the really exciting thing about this, though, okay, what happens in the Latrobe Valley, and this is what these plots show, is that by the time you get to 700 metres, you're up above 60 degrees. So in other words, you're going up more than twice as fast as you would anywhere else. Why does this matter? Because it's the drilling that costs money. And so the closer you are to the surface when you get to these temperatures, the more accessible that heat is. And you can see this is the gradient, and you can see the impact of the layers of coal in the Latrobe Valley. And I'm going to go through this fairly quickly, but this is just a cutaway along this line here, and the top one along the red line there, of the layers of coal in the Latrobe Valley that they've been digging up for the last 50 years. Okay, and you'll see the blue underneath there, that's the aquifer that we want to access. So it's a hot aquifer at about just over 60 degrees. Okay, so if this is so interesting, why hasn't somebody used it? Well, in fact, one group have. The Latrobe City Council, actually on the advice of my colleague Graham Beardsmore, when they were building their rather lovely aquatic centre, Graham said, "We'll put in a geothermal system." Now, they were very conservative, so they've got a gas system and a geothermal system. But for most of the last couple of years, the geothermal system has been running the swimming pool. We were challenged about 2 years ago, because we said, well, this is wonderful. Look, they're running it on geothermal. It works really beautifully. And so, in fact, it was the government said to us, show it's economically viable. Okay, so we do what we're told. And so we worked with the Latrobe City Council and got all the data from the swimming pool, and we worked out the mean daily heat demand. So this is in gigajoules a day. I particularly like this plot because it's a piece of science that reflects what you really know. And you can see that as you get to January, you need less heat, and then you need more when it gets cold. And we plotted the mean air temperature up the top here, and it's directly correlated, which is just not a big surprise, but it's beautifully correlated. Anyway, we were particularly fortunate to get an extremely smart economics student who also did physics, who worked with us one summer to do the economic study of the GRAC, which is the acronym for the Aquatic Centre. And so this is a full economic study that we had verified by a quite distinguished company of accountants who do this sort of stuff. And what we wanted to know was this an economically viable project? Well, we've got lots of numbers on this, but I'm just going to summarise the key numbers. The geothermal system costs $3.8 million. The payback time for that system is just under 5 years because they're saving about $700,000 a year in gas costs. That's what it would cost normally to heat the swimming pool on the prices of when we did it. But the system's going to last 30 years. So after 5 years, everything's free. The maintenance costs are about $20,000 a year, something like that, and basically the system just ticks over. Okay, and so it's really, from an economic point of view, a very strong system. The other thing is you're avoiding nearly 1 million kilograms of CO2 emission a year, which is not to be underestimated. And we've published that in a referee journal. But what we got to from this, so we thought this was a pretty good result. In fact, we thought it was a really good result. And so we started to think, well, what can we do with this? Where can we take this so that we're not just doing swimming pools, we're doing something that is a bit more adventurous? And so our question was, could Gippsland's local industrial economy be built around geothermal, basically a carbon-free energy, and essentially replace gas for those industries that use gas. And so that set us on a path to develop something that we called the Smart Geothermal Industrial Loop. You always have to have an acronym these days to make people enthusiastic. So what we did was, with some of our engineering colleagues at the University of Melbourne, we started to design a loop, and basically there's a production well. We bring hot water up from the aquifer, we run it through a bunch of industries, and then we re-inject the water back down into the aquifer. We were very clear that we didn't want to deplete the water in the aquifer. The water will go down a little cooler, but essentially it's exactly the same water and we're not disturbing the aquifer in any major way. We got data from about 6 different industries, so this is real data. Bega gave us data, you know, a bunch of other industries gave us all their energy data, and we fed that into our model. And the reason that we're doing a loop is we discovered when we looked at the GRAC that in fact we weren't using a lot of the energy that we were bringing up, the heat that we were bringing up. There was way more than the swimming pool was using. So we started to think, well, perhaps we can do this more efficiently. We also discovered that for each production well, you could, in fact, for each re-injection well, you could have 2 or 3 production wells and it would work perfectly well. And so if we're thinking about drilling costs being the major cost, you know, to have 3 production wells and only 1 re-injection well, this works really, really well, economically speaking. So this is the sort of scenario that we developed. You know, you can then work out the energy costs. And you can start, there is some electricity used in the system to actually pump the water around, so that's what this is. And we also had some heat pumps for some of the industries because we were lifting the temperature of the water up from the 60 odd degrees that comes out in that location, and we can lift it up to about 120 degrees. Okay, so a little bit of electricity used, but that can be sourced from renewable resources quite easily. But you can see it's very different from a gas system, and so this is the major plus. So then we started to think about, well, what sort of industries could we help? I'm not going to you know, obviously we can't make steel with hot water. That just doesn't work. But surprisingly, there are a lot of industries that operate up to about 100 or 110 degrees, which we can reach quite easily with this resource. And so you can read them off well enough. Food processing, greenhouses, as I said before, is one of my favourite ones. But there's all sorts of drying of foods, milk evaporation, so the bigger factory down there, we could service all their energy needs quite easily. And what's happened is that we're now in discussion with half a dozen industries whose resources are very well aligned with the sort of temperatures that we can do. Okay, so in addition to that, we thought, well, look, let's look at the cold plume that we're putting cold water or cooler water back down into the aquifer, and that will spread out through the underground aquifer over time. How long will it take to get back to our production well? And so this is actually the site that we've been using for our testing. This is Morwell here. There's our production well down there. This is where we're re-injecting here. It's about 1 kilometre difference. And this cool plume is the result of modelling for 100 years. So after 100 years, that cool plume reaches our production well and it drops the temperature of the water that we're extracting, in this particular case, by 3 degrees, which is hardly anything. Now, of course, over time, the heat coming up from the core of the Earth will warm the aquifer back up again. But what it's saying is that we could put a bunch of industries in this location for 100 years. They would have free energy after they'd paid off the infrastructure in about 5 years, and they could stay there for the next 95 years with free energy for whatever it is that they're doing. In my head, and I'm just a physicist or an astro, this is pretty good economics, okay? All right. So, what's happening in the rest of the world? Well, you may not know this, but Paris sits on a hot aquifer. It's called the Dogger, and this is a map of it. That's Paris there. And they've been using it since 1969. There's 250,000 houses that are on getting all their heating from this aquifer. Look how far down they have to go. They have to go down 1,500 to 2,000 metres. Remember, we're talking about 600 metres in the Latrobe Valley, so this is way, way more expensive to drill that far. It's coming up slightly hotter. but not much different, and it's loaded with mineral salts. So that's not so good because it clogs up the pipes after some time, so you've got to keep cleaning the pipes out. Our water in the Latrobe Valley, everything we've tested so far is incredibly clean. Okay, there's almost no mineralisation in the water, which is fantastic. And of course, because it's sitting over Paris, which is they're using it quite intensively, they're going to have to manage this, and they're now thinking about how to manage the water coming up from their aquifer. Greenhouses, I've mentioned them already a few times, but one of my favourites, and this is the Netherlands. Lots of some sort of greenery growing there. The Netherlands have a very sophisticated greenhouse industry, and they produce and export food for a lot of Europe, and they really are at the front of food production. And they now believe that 50% of the heating of their greenhouses will be geothermal by 2030. So this is just a few years away. They've already obviously got a lot, and this is an image of one of their facilities. They have to go to 2 kilometres to get their aquifer. It's a little hotter than the Latrobe Valley, but again, a much more expensive drilling process than we need. And they're replacing gas, and you know, there's a war going on that has reduced their access to the gas that they used to get. So this has put this front of mind in the Netherlands. I thought I'd pop this one in. You may not know, but there's a business on the Werribee Plains that brings warm water up from the aquifer under the Werribee Plains, because there's also coal under Melbourne and across Werribee in the top part of Port Phillip Bay. And they raise barramundi fingerlings, so little baby fish in these ponds. And so if you buy barramundi, it's quite likely that it's been raised in one of these geothermal vats under Werribee. All right. Now, this, and it goes crazy. I couldn't figure out how to slow this thing down, but you're going to get giddy if you keep watching it. So to finish up with, I thought, so I've talked a lot about direct geothermal, and of course electricity is extremely interesting. And I said you're going to have to go deeper because you've got to go hotter to get electricity. And the company that we've been talking with, and you know, I worked on a report a couple of years ago to look at this in some detail, is called EVA, which is a Canadian company in Alberta, Canada. And they have developed a system that allows them to go very deep, and then to essentially set up a radiator system where they run a fluid down, it runs through the hot rocks, it heats up, it comes up, goes through a turbine, and then it goes back down again. Now, there's some really, and they've got a working model in Alberta, okay? The fascinating thing about this system is, and because the holes that they use, they've sealed them so they're not interacting with the rocks, so they're not polluting the underground reservoirs at all, but they use CO2 as the working fluid. This is actually fantastic because CO2, if it gets out into rocks, it's positive. It turns into a carbonate of some sort when it mixes with water, so it's not a problem. But it actually works on a thermocycle. And so it cools down when they take the heat out of it, it drops down by gravity, it heats up and it rises naturally, so they don't even need to pump it around the system, which is quite extraordinary. Now, this mob are having got a successful prototype operating in Canada. They're now building a much bigger one in Germany. They've got to go down to 4.5 kilometres, which is about 150 centigrade, and they're going to build about an 8 megawatt power station with that. And it looks like this, so you can see it coming down, and then it's got a splayed out radiator that then goes around, heats up and goes back up again. So it's quite innovative. And the gas and oil industry have developed very sophisticated drilling methods, and so you can now do things like this underground quite simply. Okay, so all of that evolution is wonderful. And then finally, they also have an experiment going where they're drilling down, they're currently at 5.5 kilometres where they've hit 250 centigrade. And so what they're looking at is trying to evolve this sort of idea anywhere on the planet. Now remember I said that as you go down, it's 25 degrees centigrade per kilometre. And so when you get to 5 kilometres, you're at 250 C. That's a good temperature for generating electricity. But the point is you can do that anywhere on the planet. You don't have to be in a good location. You can do that anywhere. And so this is really what these guys are shooting for. And just to... because I stopped it. I said back at the beginning that geothermal, there's been very little investment in innovation and research. Some of our colleagues that we've been working with, the company GTET that we've been working with, on very limited resources, I might add, have actually developed a geothermal battery, which we could actually use with the resources that we have in the Latrobe Valley. So you could have your intermittent generation actually feeding into a quite simple battery system, hot and cold tanks that you can then use to generate electricity when the sun isn't shining or the wind isn't blowing. So there's lots of innovation potential and possible in this space, but it does require a modest investment, and I do mean modest. All right, so let me get to my summary. I think I'm pretty much on time. Energy generation is a complex problem. There are many aspects to it that you have to take into account, and I hope I've highlighted a few of those. And somehow we've got to figure out ways to optimise the solutions, and that's through dollars, technology, and particularly carbon dioxide emissions, which are really the most crucial thing at this point in time. There are no silver bullets. There is no one answer to this problem. It's going to take a little bit of everything. Geothermal is not the answer. It can solve part of the problem, but it can't make steel, for example. So we'll need hydrogen, we'll need other things as well. We do have enormous geothermal resources in the Latrobe Valley. The aquifer that I showed you spreads over 6,000 square kilometres. That little cold plume I showed you is 1 square kilometre. So we could have 6,000 of those in the Latrobe Valley alone. The geology of the Latrobe Valley is repeated at the back of Anglesea and across further near Warrnambool and across, in southern Western Australia. So it's not the only place in Australia where we can do this. Geothermal, hardly anybody knows about it in Australia. We just haven't done anything about it. So what I've been trying to do for 15 years is to encourage everybody to actually explore these options and put a little bit of funding into making it happen. So thank you.
That was incredible, Rachel, and from the first conversation we had about this, I'm just so grateful that you've come and shared all this with us. As you say, we don't know a lot about geothermal in Australia, and so it's actually just wonderful to have you give us this amazing overview. I'm sure there's many questions. There's 2 microphones in the room, so if you can pop your hand up if you have a question, we'll bring them up to you. I'll come in here for the first one.
The last point you just made, I was thinking about it. Why aren't the Labor Party fighting back saying geothermal to the Liberals if it sounds that good? And my second question is that question number 1, why is it the politician in the Greens? The second question is, in terms of risk management, seismic events, if a dam breaks or flooding occurs and water falls into those drilled holes and then the cold water hits the heat and then gases are created in that expansion, what consequences?
Okay. So I'll answer your last question first, right, because that's reasonably straightforward. The sort of systems we're designing are completely closed systems, right? And so, you're drilling holes that are about this big, they're encased, right? So the problems you talk about will not happen. Part of being able to re-inject the cooler water back into the aquifer means that we're not allowed to do anything to that water after it comes up except take heat out of it. And so there's a heat exchanger. It never sees the air or anything else. You know, the Peninsula Springs guys, they have a lot of trouble putting their water back down in the aquifer because you've been in it, you know, with oil all over your body and all the rest of it, so you've polluted it. But what we're talking about is keeping it pristine and sealed and going straight back in, just taking the heat out, okay? So that's the first thing. The second part, why don't the Labor Party do something about it? I don't know. I do my best to knock on the doors, and I think we do have some traction just recently. I think we're starting to get some traction in places where it matters. But, you know, industry is also very conservative about taking this up. So, you know, it's partly convincing industry as well to bite the bullet and do it. This is one of the reasons why I think greenhouses are a great place to start, because it's a much less critical path than some other industries, right? You know, if your greenhouse, yeah, it's a much less critical path anyway. Yeah.
The Cooper Basin in South Australia was the main, or most well known. I think it was hot dry
rocks. Yep.
Yeah, but it didn't work. Yeah.
No. Well. so what they were trying to do there was really quite different. So first of all, those rocks are hot. There's no question about that. They're heated. In fact, it's not the sort of heating that I'm talking about here. It's radiometric. In other words, you know, the ground is full of uranium and other such you know, elements that are producing the heat underground. There were a lot of issues around the particular what they were trying to do. But the simplest answer, I think, is low-hanging fruit. So the projects were actually quite difficult, and they had some technical difficulties. What I learned out of that was, let's do the simple things first. And the sort of thing that I'm talking about here is much simpler. Does that make sense?
I don't know. The conduction of rock is very, very poor. So it would seem that they were trying to extract at a far greater rate than they could be replaced.
That's right.
I thought the Great Artesian Basin, and the water comes out of there boiling all over the place.
The Great Artesian Basin is also a great example. It's coming out at 86 degrees, so you're absolutely right. And one of the images I showed earlier was a power plant, in fact, that has been constructed at Winton, and they can actually generate electricity from it. There's a lot of teething problems in the early stages of any industry. These aren't technical difficulties, it's just about sorting out how to do it optimally. Yes, the Great Artesian Basin will be a great resource as well. Yep. Anybody who's been in Perth, you know, they pull a lot of water out of their aquifers. It's not as warm as the Latrobe Valley, but it is quite warm. I think it's typically around 45 or so degrees, 45, 50 degrees. So exactly the same sort of idea. Mm.
There were actually two down here. I think there's one in the middle. Is that person still moved? Otherwise, there's one over the side here. You've got one of them. We've got one. You usually hand over here because I can't figure out who it was. Got one up here. There's one here. One over here. Thank you.
Yeah, hello. Thank you for the lecture. It was very exciting, Rachel. You've got physicists, you've got economics students. I think the best thing would be a marketing student. Because that will tell you what. This is very exciting. And I'm in business, and I can tell you energy has been the last 10 years is all they talk about. If you had a great marketing, campaign behind it, I think you'd do quite well.
That's a great. That's a great suggestion. So the next summer student that I advertise for will be a marketing student. So thank you.
Seeing that coal is a great insulator, does that mean that all the coal places that people are keeping up at the moment to use as coal are actually really absolutely great places for doing this?
Yes, that's exactly what it means. And in fact, parts of Europe where they also have, these similar sort of coal reserves have exactly the same hot water underneath them. Yep. So it's quite widespread.
Let's go up here next, Jen.
Yeah, I think, wow, that was powerful. I think I'm thinking along the same lines. The really exciting thing is the geothermal electricity generation because it's transportable. And if you can drill anywhere, then you can site it at the coal power plant and reuse the existing transmission lines. Because one of the biggest challenges in our energy transition is building those new transmission lines. No one wants them in their backyard. And if we can build the plant at the power station, we also keep jobs in those communities that have historically had coal power jobs. So that's my interview for your marketing student. It seems like a no-brainer. If I were a coal power plant operator, I would want to transition to this. Given that it seems like such a good sell, why are the coal power plants not doing this? What's the barrier?
Well, I mean, I will say that, we have conversations going with quite a number of the people who did or do own coal fired power plants down in the Latrobe Valley. So they are thinking beyond where they are. The people we talk to tend to be in the middle of the company, not at the top of the company. And I think there's still a percolation of information that needs to go all the way up, if you know what I mean. But look, your suggestion of doing that in the Latrobe Valley, in fact, those high temperatures are at reasonably shallow depths, comparatively speaking, in the Latrobe Valley. So probably at 3 kilometres, we'd be getting the temperatures that we need for power generation. I did a bit of a study, in fact an economic study with the same student on this a couple of years ago, and because of the current capital cost of drilling, it would produce reasonably expensive electricity, but nothing like as expensive as nuclear, let me tell you. So it's still quite cheap compared to nuclear. So if you could bring the drilling costs down, and that requires doing a lot of drilling. So if you do a one-off, it's expensive. If you had a drilling rig and you drilled 100 of these down in the Latrobe Valley, the price would come down. So this is how the economics works. But it's a good idea.
Just a few slides back, you had I thought you had the thing about the carbon cost of pumped hydro is quite high. I misread that. It was the one where you compared different nuclear and whole others.
Oh, you're way back here. Yeah.
Hydro was quite high. I was kind of surprised to see that.
That one?
Yeah, yes.
So
a bit why is it so high for pumped hydro?
Which one? Sorry?
Pumped hydro storage.
Oh, the pumped hydro. So I didn't actually look at the pumped hydro things, but all that these guys did was they found published examples and then used the published examples. And so it depended where it was, so it could have been, with the pumped hydro, it could be something to do with, how they built the system. I did look at the nuclear energy, and the thing that I discovered was that the carbon emissions, the carbon dioxide emissions for Australian uranium are way higher than most other uranium because of the way it's mined and the quality of the uranium. So all of those things feed into the numbers of grams of carbon dioxide per kilowatt hour. So you've got to go back to all the way back to each source.
I have one waiting here for a bit, so do you mind if I jump in here?
Thank you. Thanks for the talk, Rachel. This sort of energy stuff is very different from the astro work you normally do. Just wondering what motivated you to, look into this sort of stuff. Like, was it something you came across in your science, or was it more of a personal, political needing to make a change type thing?
So I was saying to Susie earlier on that actually what happened was my parents, this is sort of 25 years ago, asked me to go and speak at their church about climate change. And I said, oh, okay, I'm a scientist, I think I can get ahead of them on climate change. So I swatted up on it a bit. And I have to say, so this was pre-2000, what I discovered when I looked at the data just scared me a lot. And so that started a journey. I gave that talk at their church, and there were people there who said, oh, now can you come and talk at my school? And the Friends of the Botanical Gardens had me out, and this and that. And it was at a time when CSIRO had forbidden their top climate scientists to actually speak publicly. I don't know if you knew that was happening in the late 90s, but it was. And so here was dumb old me, and I said, oh, well, I know about Venus and what happens with carbon dioxide, so I can talk about climate change, and off I went, okay? So that was how it all started.
The first one on the side is up here, and sorry, then I know you're waiting.
Yes, hi Rachel. People talked about you sort of utilising the existing high tension power lines, putting in the Latrobe Valley would be ideal. If you wanted something of size, like a Loyang A equivalent, how big a land surface area would that require to produce that amount of geothermal energy?
Okay. Yeah, no, that's a good question, and I have to say, I mean, the question that I looked at was, what would it take to generate a gigawatt of electricity from geothermal? The Victorian usage is around 10 gigawatts, and so I thought 10%. That's actually a significant amount to do. You could do it, in the Latrobe Valley, and the EVA design that I showed you, as that evolves, you wouldn't just have one of those, you'd have to have a number of them. But the actual surface footprint of each of those is actually remarkably small, because you've essentially just got a generator, and then, your pipe's going down. So it's not too invasive compared to a lot of other things.
You can still keep your farming going.
So keep your farming going.
Sorry?
He asked you to still space to keep your farming going and you food bulk.
Yep.
Yeah.
As a astrophysicist, have you ever considered zero-point energy? Once established, it would be the cleanest energy and infinite.
Sorry, I didn't really catch that, so can you...
As a astrophysicist, have you ever considered zero-point energy? Once established, it would be the cleanest and infinite energy.
Okay. I mean, all of that is true. It's just we have some way to go before we can do that. So this, one thing that I have learned over the last 20 years is, as I've said a couple of times tonight, is low-hanging fruit. So, do the things that you can do easily to demonstrate something first of all, and then go for the more difficult problems. So, so I don't, that is a more difficult problem. Yeah.
Why?
Well,
why is it more difficult?
Actually, harnessing the technology would be more difficult. Yeah.
Right, we're almost out of time, so I'm going to take one more, and whoever it was over here who had the hand up first, I think you were.
MIT is doing some work on very good well drilling. Do you see that? Crazy. QUAISE. MIT in the States have got they're using cyclotron, I can't remember cyclotrons, but they've got microwave drilling techniques, and they're able to drill conventional drilling deep and then actually drill into bedrock.
Right. So
going down up to 20
Yeah, so these are some of the new drilling techniques. Yeah, no, absolutely, and these are exactly the sort of things that would make a big difference with geothermal. Yeah, there's quite a lot of research going on at the moment to actually do this. Yeah, it would be very promising. Okay.
Fabulous. Okay, we're out of time, and there's some drinks and nibbles out that door in a bit. But before we leave, please be very, very short. Next week, which is a panel about science, sustainability, and university. So bringing some of the topics we were talking about back into the conversation.